when you're done with your note card, if you could just hold it up, I'll come back from you. I really appreciate you giving me a little bit of thought on this, and if your name could go on it, make sure you put your name on so I know who we are, so I can actually think about who these are coming from. It's important. In terms of finishing up the little reflective write, if you want to finish that up at the end of class, that's fine. I will ask that you put your phones away just in a couple minutes. But we are going to talk a lot more about the stoichiometry process with the map. Now, if you've not seen that whole map enough, you may not remember all your conversions. But as of Monday, there was only one new conversion that we even talked about. What was the only one new conversion that we spoke of? Oh, the molarity. I'm sorry, I forgot about that. That was like a whole new unit. That was a whole new unit. So that's the first one I'm starting with. Anybody saw cards? Where you are? Okay. So the molarity is at 1. You're right. It's a new unit. But in terms of using it as a conversion factor, it actually, you're right, is a new conversion factor. We can utilize it to cancel units, which is the goal of stoichiometry is to cancel units. So if you do not use units, you are already going to fail because you will not convert correctly and you will not get your full credit. Because numbers are nothing in chemistry. Units are everything in chemistry. So, but other than the molarity, what is the other new thing we did? So that's the molarity, that's the volume solution. What was the other new thing we did? Mole ratio. So that's really the thing I'm looking for. If you have your cards folded at this point, I'll come get it soon, okay? So the only other thing we did was new for us was mole ratios, right? So if you know that your mole ratios are coming from your balanced chemical equation, then your balanced chemical equation is the very, very first thing you have to start with. So if you told me, I tried, I got frustrated, your frustration should not hinder you from continuing. Right? You should be able to write a chemical equation, write down the givens. That is my minimum expectation. If you can't do that for me, then you should come to tutoring because I'm not spending time in class going over how to write equations again because we're embedding it now in terms of the stoichiometry that we're approaching. I will talk about the enthalpy and entropy stuff that you guys took notes on, but I'm just going to hold off on that for a moment because I heard some good questions in terms of I need some help on number 4. Before I do go there, please check your work for your answers. Because if your answers are right, then your work is likely right. So 1 through 4, I'll give you guys a couple minutes. It's a little blurry. If you can't read something, please let me know. Usually answers are, for me, the least important thing, but this gives you some opportunities for success if you already have this done. So go ahead and check your work now in terms of the balanced chemical equation and everything. You can see that I have like precipitate up there for the barium sulfate, my coefficients for your mole ratios. Take a minute there. So note that I am going to start with number 4. So you should write down these answers so that you can check them later. If you want to take a picture, that's fine. I actually think I have to post on my website already because it's just a Word file on my website. But at least this gives you an opportunity to check where you are. Okay, give me a thumbs up if you've checked. Okay, which one is the hardest one so far for us? Probably 4. I figured with the molarity thing. What other one? 1, 2, or 3? 3. Okay, so I'll start with 4 and 3. I may or may not do all of these today because in terms of practice, you should know your tiny bit of struggle, and we should be able to approach that step by step, not as a whole problem. So with number 4, you have your balanced chemical equation. You did a double replacement reaction. Who feels good about predicting like the double replacements and the single replacements? Most of us should because it's simply ionic, and then you flip their 2 different ions, and then you figure out which one's the insoluble product based on the solubility rule. So most of you guys took a picture of the solubility rule so that you had an opportunity to use that at home versus my class copy here. So you have your balanced chemical equation. You saw that you had this molarity thing. So milliliters and molarity. So remember that M times V will always give you moles because molarity is the process of putting moles divided by liters. So big M is moles divided by liters. So I actually went I started at the beginning and I just multiplied all the way across. So yours may not look exactly the same as mine. but your process where you stopped and then started back up will be exactly the same. So your liters, I took 120 mils, 2 liters, so that's 0.120 times the molarity. The liters of that cancel. I took my moles of sodium sulfate, and that's what I started with in my problem. So you got to moles. That's probably the hardest part because that molarity thing is new for us. Then when you took your moles of sodium sulfate, you used your molar ratio from it says how many grams of precipitate will form. Well, you didn't know what the precipitate was until you figured it out from the solubility rules, which was barium sulfate. So you took your grams of barium sulfate to be your unknown. So you had to get from sodium sulfate to barium sulfate. And that was a 1-to-1 mole ratio, which we had from our Brown's chemical equation. Last step would get you from moles to grams, which is not new for us. It's just molar mass conversion. Molar mass of barium sulfate is 233.39. So you get your grams to be 0.28. Give me a thumbs up if you made it through that. Thank you. Okay, so in terms of the next one, I think we probably got started here. Saw that our moles of that was our starting point. Now the next one utilized a little different starting point. Oops. So we have to start again over. We can't just start with our moles that we got here. Start over and go, okay, I now have 50 mils of sodium sulfate, still the same molarity. So again, you're still doing M times V to give you moles. So that's going to start you off with sodium sulfate. But then the end question was actually more about the solution of the barium nitrate that you're utilizing. So if it says milliliters, really, one second, what you could do is you could get to liters first. So if you could remember that liters of solution is embedded within the molarity concentration itself, then I think you'll see that molarity is actually a conversion factor, and it can be just as flipped just like any other conversion factor could be flipped. So I'm going to show you that here. Question? Mm-hmm. I need some space on this one. Is that good? Okay, so here's this part B. So you take your, again, this is me taking my volume in liters and the molarity of sodium sulfate. Liters cancel, I'm in moles. Now, on the previous example, I stopped, I said equals, moles, and then I was like, okay, take a breath, and then begin again. This one I'm not stopping, because you don't have to stop if you realize that you're in moles of sodium sulfate. Nobody cares about sodium sulfate. You actually are concerned about the barium nitrate that's utilized in this problem. So then again, where am I getting these ones and ones from? Mole ratio from the Brown's chemical equation, and mine's way up there. You guys can see that from your paper. So the moles and moles gets me to cancel my moles of sodium sulfate. So if you're not labeling moles, you're in trouble. And if you're not labeling what mole you're talking about, which is moles of sodium sulfate, again, you don't know if you're orienting your conversion factors correctly. So moles of sodium sulfate cancel. That's my new conversion, which is the molar ratio. Now the last step is the barium sulfate moles has to cancel, but I have to get it to liters. Well, the only relationship between moles and liters of solution, don't think 22.4 liters. That aligns with what? Gases. Thank you. So this is that conversion that is actually the molarity. But what have I done to the molarity here? I flipped it because I needed to get moles of the barium sulfate on the bottom and the liters on top, because that's my question. My question was volume. It's asking for milliliters, which is just liters and then converted. But don't forget that molarity is moles per liter. That number that the molarity is saying is describing the number of moles in the sample. So this is a really dilute solution because it's like 0.01 moles per 1 liter solution. It's just like water. It's very dilute. So this is the moles that will cancel, getting me to liters of solution. And then my final step would be get to what? Milliliters by doing what? Multiplying it by 1,000, so 1,000 milliliters per liter. Okay? So that new molarity thing is the only weird, it's adjustable, you can flip it if you need to. Can I take some questions on this one right now? Yeah. Sorry, this was my one typo, I think it was 50. It's my marker, yeah, it's good. This is the one that I think I had to recalculate, but I already had this crafted, so I didn't want to miss. I think it is 50. I think that's what I had on my answer key. I'd have to double check. Questions on how to use molarity? Okay. Speak now, guys. You get asked questions. The next one is you're given the moles of precipitate, which in this case you did have to know the precipitate was barium sulfate based on the solubility rules yet again. And then it said how many grams of the other product will be formed. So then the other product is being cryptic because it's trying not to tell you who the precipitate is. It's trying to make you use your brain because you have all that knowledge. So what is the other product here? Sodium nitrate, right? So sodium nitrate is what's asking for. So you might need to write that down for yourself because it's not as evident in the question itself. My board is a little bit off here. So you have your 2.5 moles of precipitate, which again was barium sulfate. Your grams of sodium nitrate is what's asking for. So you have to go from moles, and you're already in moles, so it's easily getting you from point A to point B, which we use the what here? Mole ratio from the balanced chemical equation, which we had above. So once you're in moles, your half the battle is done. You just go to the other moles by using the mole ratio. And then the last step would be getting from sodium nitrate moles to sodium nitrate grams, which is 85 grams per mole. Cancel your moles out, grams remain. 425 grams is what our answer should be. Yeah.
I got 420 because I only used 2 substance.
420, yeah. So I'm process here. So it's actually should be 430 because you'd round up.
Yeah. Well, I got 424.97.
So your molar mass probably was to more sig figs by looking at your periodic table. Sometimes what you guys will find is our answers will be really close. I have like most of the periodic table memorized with the masses, so I just go with my memory. So if that's like 85 point what for you, or 84 point?
84.994.
Yeah, so it's going to be a little bit lower. So then if you put 420 grams or 430 grams based on your first initial answer and then rounding, I can look at your work and watch your process. It's more about the process necessarily than the final answer. But grams should be grams of sodium nitrate. Okay, so that's number 3. That definitely was the hardest one because you use that numelarity thing. Number 4. I'm going to scooch back to number 3 just to give you some insight based on your questions, but I'm not going to go over the entire question right now. So if you need help, you need to come after school for tutoring. Note to self, come after school for tutoring. Can let me open that door for him? Thank you. So first off, we have done the synthesis of aluminum hydroxide from aluminum oxide and water. And this is a reaction. This is a synthesis reaction that you can look at from your notes from last unit. If you're not looking at your notes, you're probably not supporting yourself enough because that's kind of me on paper, right? So if I've already given you all that insight, you need to utilize it. After you get there, you can process through moles of the product being aluminum hydroxide, starting with your 98 grams of aluminum oxide, your initial reactant, grams to moles, moles to moles, moles is your final answer. Step 2, part B, how many moles of water? I'm videoing right now too, so if I'm going too fast for you, you can watch the video. If you're starting with your moles of water and you're getting to moles of, if you're questioning about your moles of water and you're starting with your moles of aluminum, it's a mole to mole conversion, which is one step. That's your balanced chemical equation again. So your moles of water, or what you're getting, and your moles of aluminum oxide should cancel. One step. Last one, which I think was the part that some of us had some issues with. How many grams of the product? Again, it's being cryptic because it's trying to let you have a chance to predict the products, which was aluminum oxide in this case, are formed when you have 67.2 grams of aluminum oxide. So in that case, it doesn't matter it's being formed or it's being reacted. It's just that's your given, your starting point. And if you label your unit, you'll notice that you need to cancel your grams to get to moles of aluminum oxide. And then nobody cares about aluminum oxide. We were trying to get to aluminum hydroxide. So what's this right here? 2 to 1 mole ratio. And then your mole ratio gets you to moles of aluminum hydroxide. And then you can use your molar mass conversion to get to grams. Question?
Just for clarification, the balance
Yep.
How?
Because it's a recipe of how do these different reactants and products relate to each other.
Where do you get the numbers off of?
From the coefficients. So this 2 and 1 come from this 2 and this 1 here. The coefficients, and does everybody have their mole map in front of them?
Yes.
You should have written that down in terms of writing down the notes from Monday. Gosh, I feel like it was a Friday already. If I can actually get back there, it will happen. I promise. It's way up here. Oh, there it is. Okay. Mole ratio from balanced chemical equation. If you did not write coefficients there, go ahead and write that now because that's the only way you're going to remember. That's your support system at home is your notes. and the videos and online. I mean, there's tons of resources, and if you didn't get started, that's on you. Okay, so I'm going to give you guys a second to ask each other some questions based on anything you need to, and then we're going to move on to some help limiting reagents. So it's an extension of what we did on Monday. Okay? You need to grab a calculator, you can grab a calculator now. We're going to do that. You guys have little cards? Little cards? Oh, thanks. I'm coming to you. You're good. All right, back to me. Our here off topic conversations now. So, in terms of talking about what we did last Monday, we're going to be applying that to the bigger picture. Okay, so the bigger picture is something related to efficiency in chemical reactions. So let's say I want to make a product, and that product, it's got some other stuff mixed in because of some excess reagents that were never used or some contaminants that were made. So if I want to optimize my amount of product, and this is done like in industry a lot, think of even like food. You're making something and you have a lot of leftover stuff and it's all contaminated. You don't have to eat that, right? So in terms of making a product, we always want to make 100% of our product that we want, which is called percent yield. So a percent yield being like 50% yield, what would you say about that person's process? They're not very good at it, right? Or maybe it's just not very efficient because it makes a lot of different stuff, not necessarily the product you want. So we all want to make 100% yield, or really close to it. And the percent yield is just a ratio, which we deal a lot with math and ratios, right? Of something that we actually make in the lab to what we think we should be able to make in the lab. So my description of theoretical yield versus actual yield, which you did see on your reading guide 12, is theoretical yield is like la la land yield. We're like, if we were in perfect conditions, perfect world all the time, the land of make-believe, which, because that's not the real world, we would be able to make what we think we should be able to make. And this is something that you always will calculate on paper, because we can show theoretically how much product we should be able to make in a reaction on paper by doing our mole conversions, gram conversions, and so forth. But remember, if I'm talking about yield, I'm talking about a product. So you're not generally going to be talking about yield of a reactant, because those are being used, not yielded, not produced. Okay, so this is la la land yield. But then when we actually go to the lab and we actually do this reaction, and we actually collect the data, and we actually collect the mass or the volume or whatever, that's your actual yield. So this is what's physically made in the lab. Or I'm going to have to tell you on the paper, I'm like, oh, Margaret had 9.57 grams of yield here when she did the reaction lab. So I might have to tell it to you within a problem. But these are the two different terminologies we'll be using to describe yield. But then actually to calculate percent yield, what you have to do, can I go forward? Yes? What you actually have to do is actual yield over theoretical yield times 100, and that will give you your percent yield. So if you want to be an awesome chemist or an awesome chef, baker, or whatever you're trying to produce, and you want to make the highest yield, you're really going to have to do a great job in your processing, which is your reactions in the lab, or in terms of making something, whatever it is you're making. So you want to have a lot of actual yield. But if your actual yield is higher than your theoretical yield, something's gone wrong. Because if you're making more than you theoretically should be able to, doesn't that sound like maybe kind of impossible? If not, you're magical, right? You're either magical or you've done something wrong. So generally, actual yield is less than theoretical yield in the real world. If something else has happened, it's probably due to contamination. Yeah.
Will there ever be a chance where there isn't any contamination, the actual yield is greater than the theoretical yield?
No, because that means you're making you're disobeying the law of conservation of matter. You're making new atoms from the universe that the universe doesn't have. Yeah, it's usually due to contamination, to be honest. Or you haven't dehydrated something that there's like just little things that could happen. So in terms of the mathematics behind this, you will have to make sure that your units are either in moles per moles, grams per grams, or liters per liter. Whatever you use, it's up to you, but it must be the same units on top and bottom so that you don't have any miscalculations. Okay, so I'm going to skip this joke for a minute. I have another joke for you. So in one of the first labs we do in AP Chem, they synthesize this crystal called alum. It's not aluminum, it's just like a crystal. It's called alum. It's like a potassium sulfate dodecahydrate. Anyway, so they have to synthesize it, and the challenge is they have to make the best percent yield. So their goal is to make sure there's no errors in their lab procedures. It's a 2-day lab. It takes them a full 2 days to do it. And then on top of that, there's another 3 days of analysis of their crystals to see how pure they are. So I'm training them to be chemists. So their goal is to like 99% yield. Well, that's one group, they were like, I got 113% yield. I was like, no, you didn't. There's no way. Because in that case, they had a lot of water left over in their product. It wasn't pure. So in the respect to that, they're always trying to be a boss at purifying and making the best percent yield. So, Bromo boss at purifying, percent yield, 9.63%. That's the joke. Is that good? Is that good? No, not good. That's like horrible. No. And then lab grade based on percent yield, spend an hour pathetically scraping every last grain of product off the glassware table and the floor. And that has happened. One of my students, they spilled all their crystals all over the table, and it was liquid, and immediately at the table it all crystallized. So they're scraping. They're like, I need this for extra credit on my lab grade, because that is it's a rough lab, so I try to help them as much as I can. All right, so that's my jokes for today. Let's go ahead and process how do we apply this to a situation in the lab. So, question, what is percent yield? Stop. What is the formula for percent yield? Okay, write that down for yourself. Actual yield over theoretical yield times 100, right? Percents are always times 100. When, and let's kind of just process this first, 14 grams of magnesium chloride decomposed and 3 liters of the gas are collected at STP from decomposition. Boom. You've got a lot in your head right now, right? So let's break this down into achievable chunks. When 14 grams of magnesium chloride decomposed, what does this mean I probably should do? Write a balanced chemical equation of what? Okay, well, don't put the 14 in yet, right? That's just like some information we might need to calculate, but it's not in the equation. What's the equation? Okay, so you're writing this down with me because you're going to want this for later. Magnesium, what's magnesium chlorate? ClO3 parentheses 2. You should know your polyatomics, right? So chlorate is ClO3, crisscross the charge of magnesium down. All right, so decomposition of magnesium chlorate. What do chlorates, metal chlorates, always make when they decompose? So metal chloride and oxygen gas, our friendly gas oxygen, right? Okay, so I'm going to go ahead and make oxygen gas, because I know how to write that as O2. What's what's the metal chloride? Good, it's magnesium chloride, which is MgCl2, because you're crisscrossing your charges. Okay, and then what do I need to do to balance? 3 in front of oxygen, and that's it, right? Yeah. So there's 2 times 3, that's oxygen of 6. 2 times 3, oxygen 6. Chlorine 2, and then magnesium. Okay, so we got this. That's helpful, but we're not sure what to do with it yet, right? So I also have this 14 grams. I'm just going to write that down here just to hold my information so I don't have to keep reading my question over and over and over again. So I got 14 grams of magnesium chlorate. And what? 3 liters of what? Yes, now we know it's oxygen because it says the gas. You're like, what's the gas? Well, the gas is oxygen. It's collected STP from decomposition. Okay, so what is so important about this right here in terms of percent yield? What do you think that is? That's the actual yield. They're actually saying this person collected in the lab 3 liters of oxygen gas. Label that actual yield so that you remember it's going to go up here when we get there. So check, we have half the problem solved. It's right here. What are we still looking for then? Okay, so theoretical yield of what? It still has to be the same unit, right? This up here is 3 liters of oxygen gas. So this down here is going to be unit of what? Liters of oxygen gas, but from what? Who's making it? Oh, yeah, from what though? From what chemical? This decomposing, right? So I need to say, I have this much magnesium chlorate. I need to take it from here and produce gas, and I need to convert that to liters. So I'm just doing stoichiometry. That's it. So this is what I'm starting with. I can't just plop the grams of magnesium chlorate up here because that's not the same unit. I need to get the magnesium chlorate. My given, I'll label this like we did last on Monday. My given is magnesium chlorate. My question is liters of oxygen gas. Now, if you start with your grams of magnesium chlorate, what do you have to do first? You can't really use grams, right? That's not helpful. Grams to moles, right? So you're writing down your process. Let me process it first, and I think I'm going to answer all your questions, I think. But let me know at the end, okay? So, if I have my 14 grams of magnesium chlorate, you're telling me I have to convert to moles, right? So, somebody calculate the molar mass of that right now. Magnesium weighs 24.31 plus 70.9 plus 96, right? Anybody? I think that's a little off. Say again? Can you tell me the molar mass? I need the molar mass. I got it. You guys can double check this. 24.31 plus. Anybody? 1 second, Caroline. You just need to calculate because you need to be seeing your periodic table. You need to be seeing these numbers. You need to be looking at the periodic table 5 times a day so you can find your reagents. So you're not hunting for them whenever you actually need them. I'm trying to enforce these best practices and skills on you because in the end, it will benefit you. It's not benefiting me at all here. I can do this, but you can't. So I want you to feel good about what you're doing. Yes. Molar mass, anybody? How are you getting your molar masses? How much you're plugging your calculator? 191.21. Anybody got 191? Thank you. You guys need to double check. There's 1 magnesium, it weighs 24.31. 2 chlorines, which weigh 35.45 each. And then 3 times 2, so that's 6 oxygens, so that weighs 16 each. So that's 96 plus 78.9 plus 24.31 is 191.21. Okay, so yeah. So you got your magnesium chlorate from grams to moles by using your molar mass conversion. Is this new? No. You've known how to do this for 2 weeks at this point. Now, nobody cares about magnesium chlorate. What are we trying to get to? We're trying to get to oxygen, right? The yield, the gas that we're yielding. So now I need to pull the information from what? Bound chemical equation. That is the relationship that we know. This relationship is 1 magnesium chlorate for every 3 oxygens. So how do I put that here? Say again, Jacob. 3 moles of oxygen over 1 moles of magnesium chlorate. Thank you, sir. Okay, so I'm going to start calling on people, so be ready because you guys are dead in the world right now. All right, so ignore this right here. Sorry, this is kind of just in the way at this point. Okay, so we have magnesium chlorate has canceled, moles of that anyhow, and then now I have moles of oxygen. Kyle, what's my last step? Okay, so how do I do that?
On top,
Mm-hmm.
22.4.
And this is something you just memorized, right?
Yeah.
And that's liters of oxygen per
1 mole.
Right, and that's our molar volume conversion that we've known for 2 or 3 weeks at this point. So moles of magnesium chlorate, moles of oxygen can now cancel with moles of oxygen. We get to liters of oxygen. Please, everybody calculate that right now. Use your calculator. 14 divided by 191.92. Make sure everybody's catching up real fast. Times 3 times 22.4. Caroline.
3.28 liters of oxygen.
3.28 liters of oxygen. Okay. Double check your math real fast. I usually go with majority because I'm not calculating. You guys are my calculators. 4 point what? 92. Okay, 92 liters of oxygen. It's probably just a slight number off there. All right, so what did we just calculate? Don't say liters of oxygen. We have said, theoretically, if 14 grams of magnesium chlorate decompose, theoretically, they should be able to make this much oxygen. So this is my theoretical yield, and this is what this poor lab student did. They only collected 3 liters. Oh my gosh, 3 liters versus the 4.92, that's almost 5. What's approximately the percent yield? What's 3 over 5? Don't calculate. Estimate. About 66%. Let's actually calculate now by plugging it in up here. We had already set up, said 3 liters of oxygen was what they had made. 4.92 liters what they could have made. What's that percent? 69%. Something like that. Okay, would you want them in your lab?
Wouldn't it be 61%?
61%. So, would you want them in your lab or in your industry? I mean, it's not that bad, but they got some work to do, right? We really want them up upwards of 85, 90%. Okay, so what's the new thing for us today on this one? Percent yield, but identifying the problem. When you're reading it, can you find out what is the actual yield, which has to be given to you, right? You're not going to get up and go in the middle of the lab and go, oh, let me go calculate, let me go figure out how much actual yield I can actually make. I'm going to tell that to you in the problem. So most of these problems are you're going to be calculating the theoretical yield and then plopping it into your equation of percent yield and then calculating. All right, go ahead and get up and get a stretch break in here real fast. Go talk to somebody about what you're doing this weekend and your long weekend. Get up. Get up, get up, get up. Before we start the next part. If you have s'more stuff, please put it on the back lab station, but you must label it with your name. If you have s'more stuff, label it with your name.
You have 2 pieces of bread, right? One
So you still want some more stuff as well? Did you ask me to bring some more stuff tomorrow?
All right, Ian, get back to your desk for me.
2 weeks later. You get 2 different pieces of bread. You get 3 different pieces of bread and chill. Then you like fill the columns and then flip the pieces of bread. Now you can combination.
All right, Caleb, I'm going to volunteer you, man. Calm down. I need you for this. Will you be my sandwich maker? Oh my goodness. Get into your desk, Caleb. Yeah, thanks, man. Come on down. All right, so Caleb. All right, thanks guys for that enthusiasm. Okay, come on this side. You can come on this side. So I need you guys to quickly tell him how to make the perfect peanut butter and jelly sandwich. Let's go, Surprise. Perfect peanut butter and jelly. He needs a recipe, basically. So how much bread does he need? 2 slices of bread. Okay, you got this. 2 slices of bread. This is important. And some like just 1 serving of peanut butter. Okay, and 1 serving of jelly, and that's gonna make happiness in a sandwich. Okay, 1 sandwich. Okay. All right, Caleb, you got this? You ready? Here's my okay, let me explain this to you. These are my pieces of white bread. That's all I can afford, guys. My pieces of servings of peanut butter, okay, and my servings of jelly. Okay, man. Make as many sandwiches as you can. You ready? Ready, set, go. Okay, it's your mom. Peanut butter and jelly. Yes, let's go. Come on. He's got this. Come on, Caleb. Do it fast in there. Let's not full sandwiches only on 1 square, guys. What do you need? Okay, 2 slices. Okay, here we go. Here we go. Keep going. 2 minutes, man. Let's go. Let's go. Come on, guys. Give me some enthusiasm. 2. You're at 2. You need 1 for everybody. Let's go, Caleb. Let's go, Caleb. Caleb, you got this. Okay, we got 3. You got enough for these 3 people here. Let's go. Keep going. Okay, we got another one. And
A half percent.
Make it bold.
So, but we, it
This
doesn't, no, because that's actually,
Make a
that's
wrap.
not full, right? So what happened, guys?
We ran out of bread.
Oh, no. What was the product we were trying to make? PB&J, right? But what held them up?
Bread.
The lack of bread. Okay, so the lack of bread is like, no, we ain't making no more peanut butter jellies. But what else? Look at, he's got all this peanut butter and all this jelly, right? These are, what's a good term to talk about these, their nature of how much I have of this? I have a lot of excess of peanut butter and jelly. What did I run out of? Bread. What would be a good term for that? I don't know. It's on your, it's on your reading guide. And it's on your crossword. Thank you, Caleb. Thank you, Rebecca. Thank you. Signature for there. Okay. So I'm gonna go ahead and give this to you. It's limiting. This is the limiting reactant because they ran out of the bread. Poor Caleb was like, "Can I make half sandwich?" We were like, "Nope, it's gonna make a full sandwich." That's the recipe that we came up with. Thank you, Surprise. But then what was true about the peanut butter and jelly? What was the term we used? They were in excess. Okay, which of these determine the production of the sandwiches? The limiting reagent controlled the sandwich we made. Okay, so if you want to make a certain amount of a product, you'd have to make sure you have enough of everything. But not too much of everything, because then you're gonna make it. You're gonna have one way in excess and one's way limiting. You probably want to have stoichiometrically equivalent amounts. That's kind of the term to use. Stoichiometric equivalent, meaning you have enough of everything. But if you had to have something in excess, and you're in industry and you're trying to make something, would you want your most expensive thing to be in excess or your cheapest thing to be in excess?
Cheapest.
Why your cheapest? Because what's probably gonna happen to the excess stuff at the end? Lost, it's contaminated, you're going to wash it down the drain, you're going to throw it away because it's like been used and it's got all this other junk mixed in it. So you always want to try to use your cheapest one as the excess because that way you get the most yield and cost efficiency of your product. And so that's what they use. They have to do the math to make sure they're making the best choices for their products. And so we're going to talk about it in terms of chemical reactions. Don't roll your eyes at me. You got this. I need to go ahead and get this bit in front of you because it's going to take some couple days to process. And so if you can process it today, process it tomorrow being Thursday, process it Friday, you should be good by Monday. If I start you too late, then it's hard to process everything. Now, of course, you can abbreviate this. These are vocabulary terms that you've kind of been exposed to. But you'll know that I'm going to probably do 1 or 2 problems after this, and that's it. So I'm going to support you with the basics so that you can practice on the current. So this is related just to our peanut butter and jelly sandwich, just like it would be related to a reaction. The limiting reagent, or the limiting reactant, is another way to say that. Reagent is just a fancy word for reactant. We call it the LR. So limiting reagent, I'm going to refer to it as LR from here on out. And it's the process of knowing that there's one reactant that's going to run out first. If you run out first, you're controlling the amount of product that can be made. So it's the kind of the most important thing to know. It's really important to identify this because that's the one that's controlling your reaction. And I'll also say it runs out first. Then you've got a whole nother slew of reactants. It could be 1 or 2. Like I had 2 reactants from Caleb's example with peanut butter and the jelly. They were both in excess. And so they're just left over at the end. And so you want these to be the cheap ones so that you don't waste your expensive stuff, good stuff, from your chemical processes or your chemical reactions or your chemistry examples.
Would this not be a thing since we balance chemical equations?
So that's right, we do balance chemical equations, but I don't always say, let's say I balance a chemical equation, I have 10 grams of one reactant and 10 grams of another reactant. But if the ratios are a 1 to 2 ratio, that means I need double of the other one, right? So I would need 20 grams of this one, or I would need a stoichiometric equivalent. So like the grams that we give are not necessarily directly related to the moles that we need in the reaction. That's what we're going to start with. We're going to start with figuring out how many moles we have. So it's not always, it's just equal. We'll talk about that. So the very first thing we always have to do is identify the limiting reactant, because that's going to control the entire rest of the problem. It's going to control the entire reaction the product's made. Well, there's a process to that. The first step in trying to figure out the limiting reactant is to convert both reactants to moles. So this is where now we're going to have two givens. We haven't really had two givens before. We had the whole molarity thing where it was like, oh, I'll give you molarity, the concentration, and the liters, but that really was just one thing to get you to the point of moles. At this point, we're going to have two givens where we get to moles for both. So we'll have 2 moles to start with. Then you're like fighting with yourself. Do I want to take this moles to get to product, or just take these moles to get to product? That's the process we're going to learn how to do today. So the process is just basically comparing the ratio from the balanced chemical equation to determine who is going to run out first, who is going to stop the reaction. So I'm going to use a lot. I'm talking a lot because I want to give that nail into your head that there's some things we have a lot of, some things we don't have a lot of, and that's going to determine our end product. And after we determine it, we have won the battle. We've determined the limiting reagent. We're just going to use that to solve our problems like we have been as of Monday and today so far. So I'm starting us back further than we ever have before. That's what we're doing. This is the whole process, the whole shebang. This is the pinnacle of chemistry. Okay, you can ask anybody. It's the pinnacle of chemistry. So then you have a quick example of sandwiches. In my hamburger example here, who is the limiting reagent? Can you see? So I've got 3 burgers, 4 sandwich things, some cheese, and some tomatoes. Who's my limiting? The burger, right? The meat or the veggie burger, whatever it is. And then who's my excess? Buns, tomatoes, and cheese. But there are different amounts of excess, which is why that whole starting with the moles is important, because that gives us our ratio. All right, so I'm going to show these through examples to you guys, okay? So first step, I want you guys to write down your balanced chemical equation. That's always our first step. And I need some space over here because I need like 2 boards to do these problems. This will take a lot of paper. So this is you want to leave yourself some space. Annotate what we're doing if it helps you with your processing skills. It's going to be very nice when you can actually look back at your notes and help yourself solve problems. And what's iron's charge most of the time? 3. Okay, iron's most of the 3, yes. When you have to write your reaction. All right, so what's your reaction so far, guys? Reaction? Rishi, go ahead. Okay, give me the first part. Fe. Okay. So, and this is Fe. This is Fe3, right? So that 3 gets crossed over here. So iron 3 nitrate and copper gets booted up to the coal. Okay? And then we need to balance it. So I think I need a 3 here, a 2 here, a 3 here, and a 2 there. Yay. Okay, so we got our balanced chemical equation. Step 1, write down like maybe the top of your paper, your steps, so you're remembering this. Balanced chemical equation. Step 2, moles of both reactants. So in the question, it gives us 3.6 grams of iron, and then it gives us information about copper 2 nitrate. 5 milliliters of 0.51 molar copper 2 nitrate. Okay, so this is the first time we've ever seen 2 different quantities given for 2 different reactants. So we're going to start with this, and we're going to get them to both to moles. Well, the first one's probably easy to get to moles. If you start with your 3.6 grams of iron, how do you get to moles? Molar mass, right? So you're looking at your periodic table, look for iron's molar mass. So I've got a couple people that are very good at participating. I'm going to ask for a couple. I'm going to ask for people, so get ready, okay? 55.85 or 84. I'm not sure what we said. Every periodic table is different. Go ahead and calculate that, and then get ready. So I'll ask for someone else to give me that answer. You should have a calculator in front of you. So 3.6 divided by 55.85. Audrey, you got me? 0.0644. Can I get one more sig fig? 5. Okay. So I'm not even going to round yet. I'm going to keep them all out since there's no rounding error in between. So label this right now. Label it have. I have this many moles of iron. Okay, that's how much we're starting with. All right, so then you're going to take your second piece. And how did I get to moles from these two pieces earlier? Chloe, how did I get to moles from that earlier? This is from like Monday. It's okay if you can't remember right now. So let me raise your hand. Nick. Okay, so stop there for a second. So 5 milliliters is how many liters? Can you do that in your head? 0.005, right? You're dividing it by 1,000. You're bouncing decimal back 3 places. You cannot do that in your head. Please write on paper. Don't get that little single step wrong. 0.00500 liters. Okay, so I've got liters. I'm doing a separate step. Yep, I have my moles of iron, and that step, that's half the first step. How do I get to moles? Rishi. Say again? So here we go. That's the big mistake, right? Liters of gases are 22.4 liters. This is not a gas. This is a solution. Solution concentration gets me to moles. This is M times V. Big M times V. This is my V. This is my liters. That right there is my 0.51 moles of copper 2 nitrate. And that's per liter. So my liter concentration will cancel, and I get 0.005 times 0.51. Someone calculate that for me. Kim, you got me? .005 times 0.51. 0.0025. 255 moles of copper 2 nitrate. Okay, guess what? This is also how much I have. All right, so now we actually found how much I have of both of my reactants. The next step on your process, look back at your notes from the last slide. What does it say to do? Compare using what? Okay, so use ratios and think. This literally means to think about and talk to yourself. I talk to myself on these all the time. So guys, if I have 0.00255 of this, how much of the other reactant do I need to fully react it off? So for example, if I have 2 pieces of bread, how much peanut butter did I need to make a sandwich? 1. I need 1 peanut butter. So you're comparing it because that one's easy. I have 2 pieces of bread. I need 2 pieces of peanut butter. If I had 4 pieces of bread, how much peanut butter would I need? 2. And you're doing that because you know your ratios. Well, these ratios are a little bit foreign to us. It's hard to think about. But if you have 0.20 or 0.00255 of this, I require 2 to 3 ratio of the iron to the copper to nitrate. I require 2/3 of that amount. So instead of always thinking about it, if you want to write it down, the way you'd write it down is I require, I'm going to kind of write it over here to the side. I require a, what was it, 2 for iron? You guys have your ratio? Okay. Oops. 2 moles of iron for every 3 moles of copper 2 nitrate. So sorry, I'm squeezing it there, but you can write it for sure on your paper. Write this on your paper. Write this on your paper. Write this on your paper. I will wait, and if I only get through one problem because I'm waiting, make sure you have a very, very, very good problem. Okay, so I have this much copper 2 nitrate. I require or need a 2 to 3 ratio of those reactants to make it fully react. Okay, so if I multiply this by 2 divided by 3, someone tell me that answer? 0.0017 moles of what? Iron. Do you guys see that we actually set this up so our copper 2 nitrate would cancel? So basically what she just told me was this. So she said we had this much copper 2 nitrate, we multiplied by a ratio of 2 moles of iron to every 3 moles of copper 2 nitrate, and that should equal 0.0017. Does everybody see how we calculated that? It's just because we are doing the moles of iron. So I'm gonna do the other one too. I'm doing both of them. I haven't gone halfway there. So the moles of copper 2 nitrate that we have, we cancel with the ratio. And this right here, label this exactly as I am, label this need. So basically what I've said to myself is I need this much iron to react with all my copper 2 nitrate. I need this much iron. How much iron do I have? Okay, so you're pointing at these two numbers, 0.06 versus 0.0017. What would you say in my situation? Will I be okay, or am I going to run out of iron? Tell me why, Jillian.
Because your amount of iron you already have is a lot more.
Right.
Relatively a lot more.
So compared to my copper 2 nitrate, how much I have, and I require X amount, I require this much iron to fully react with all of that copper 2 nitrate. I only need 0.0017. Man, I got tons. I've got so much more, because that's 0.00, that's 0.0. So am I going to run out of iron, or am I going to have excess of iron? I'm going to have excess of iron. Excess. Please put excess above your iron so you don't forget that thought. You just have that eureka moment. So this one's my excess. My other one has to be limiting reagent. And I'll prove it to you as well. So this is what Chloe's like, why am I using copper 2 nitrate but not the iron? You just got to start with one. And I started with that one just by chance. So same story, different guy. I have this much iron. How much copper 2 nitrate do I need to react with it, to fully react with it? What am I going to put here? My ratio, I heard it, ratio. What's my ratio of iron to copper 2 nitrate? So 3 to 2. 3 moles of copper 2 nitrate react with every 2 moles of iron. So if I have 3 moles of that and 2 moles of that, that basically means I need this times 3 over 2. What is that? 0.0966 moles of who? Who do I have? Who am I talking about now? Copper 2 nitrate, right? Because my iron, moles here and moles here, they cancel. So this is how much, label it for yourself because you will forget once we see all this math in here together, jumbled together. I need this much copper 2 nitrate to react with all of the iron that I have. I need this much copper 2 nitrate. How much copper 2 nitrate do I actually have? So look for where I have, and look where I have copper 2 nitrate. Yeah, look guys, I have, let me grab a marker here. I need this much copper 2 nitrate. I only have 0.002. What's going to happen to the copper 2 nitrate? It's going to run out. Do you see how talking to yourself about the have and need makes sense? And it helps you see who's my limiting reagent. So now that I know that copper 2 nitrate is my limiting reagent, the battle has been won. Okay, that is literally the hardest part, is to walk through, bounce your reaction, get both your moles, compare your moles with your with your ratios, and then talk to yourself and go, I'm the LR, I'm going to run out. I am the excess because I just have excess. So now, what does it say to do next on your steps that you wrote down for your instructions? Solve using who? The LR. So now don't we have the moles of the LR already determined? How many moles of my LR do I have? I have, say again? Where does it say have? And where does it say your limiting reagent? Anybody? Read your work here. right, this is copper 2 nitrate's my limiting reagent, because I just determined that. I wrote it on the top of my paper so I wouldn't forget. That is how much I have of it. So I'm going to start with that number to actually solve these problems. I haven't even read the problems, but I know we've determined our LR. So this is my LR, so I'm going to start with 0.00255 moles of copper 2 nitrate. Wherever I'm going, I can get there because I know my starting point now. This is basically where I start my problem. So let's go back and read the problem because I don't even know the problem at this point. What's the limiting reagent? We just figured that one out. We said it was copper 2 nitrate. So the real next question is how much copper will precipitate from the reaction? Okay, so what is this asking me for? What grams of copper? All right, so let's go ahead and look at the ratio. Mine's way at the top of the board. Yours on your paper. Sorry, I have to keep scrolling a lot. So if my question is grams of copper, let's just talk through this first. I'm starting with my LR in moles. All right, I'm already in moles. I have moles. What do I have to do next? But I have moles of copper 2 nitrate. I don't have grams. I don't have moles of copper. Okay, so you're going to take your moles of copper 2 nitrate. You're going to go from mole to mole using what? So bounce equation, 3 moles of copper for every 3 moles of copper 2 nitrate. So we're from mole to mole. And now I'm in moles of copper. What's my next step? Go to grams of copper. Write that down. Start with your starting point that we already started with. And I'll write it down too, but I'm just going to kind of make sure you can kind of see everything that's above here as well. So this is all old school tests because we've done the stoichiometry conversions. So this is from our classical equation. You should be looking for copper in your periodic table. Anybody have a final answer for me? Give me a second. Brittany, can you calculate that? Or do you already have that calculated? Say it one more time. So tell me where you are here and then I'll kind of help you out. So do you see where we got this from? So that's just all our pre-work of finding the limiting reagent. We start with that. We had our moles. The only, when nobody cares about copper 2 nitrate, we actually want copper. So we had to take our moles to moles of the other things. So that's our A to B, that's our mole ratio, which we got our 3 from 3, 3 to 3 from our coefficients and our bounce equation. And Margaret, do you have your answer?
Yeah.
0.162 grams of copper. That's beautiful. It's good. I got 6.5, but it depends on your periodic table. And I started with different sig figs. So, in terms of getting that, basically we just said, if I have this reaction to begin with and I want to get X amount of copper, like say you actually want copper, you're trying to precipitate all the copper out, you can control how much copper you make based on your initial reactants. So we made copper. We made a little bit of copper, not very much. Last one, and this should be the last one for me right now, actually today, is how much of the excess reactant is left over. So in our example up here, how would I figure out how much peanut butter and jelly I had left over? Because those are the excess ones, right? How would I just basically say I have a starting point and I have an end point, how much is left over? What mathematically would you have to do? Subtract what? Okay, so your starting point is what you have, right? And you would figure out how much you used, which we didn't say the word used here, but what did we say? We didn't say used, we said need. So if you figure how much you have, you've already done that, right? If you figure how much you need, haven't you already done that? What do you just have to do with those numbers now? Subtract them. So writing your work and labeling it is so important. If not, you're going to have to double up and do your work twice. And nobody got time for that, right? You got to make sure you label. So who's my excess again? Iron, and you've labeled that top of your paper. So how much did I have of iron? How much did I have of iron? Okay, it's not, you're not pulling out of your butt, right? It's on the board, it's on your paper. 0.06455. So 0.06455 moles of iron. And this is my question on excess leftover. Okay, so I took how much I have, and I'm going to subtract what? Yeah.
We've got 0.0644.
Sorry. All right. How much do I subtract there? Rishi? Where are you getting that from? The need of the iron that was required to fully react with all the limiting reagent, right? So that's how much is used up. That's how much is used up from the initial amount of iron I started with. 0.0017. So minus 0.0017 moles of iron, and that again was how much I needed. If you were labeling your work as I was asking, so that you could actually follow my language here. So that minus that gives me what? 0.06275 moles of iron. Okay, now this question, it's at the top of the board. It says how much excess is left over. What is much generally referred to? Grams. So it will be our last and final step. Convert this final bit of moles to grams. And what's the molar mass of iron?
50.8.
Right, so 55.85 grams of iron for every 1 mole of iron. And that is 3.15. Huh? Double check. 3.5 grams. I think, sorry, dyslexia sets in sometimes. 1.5 is 5.1. I probably would have actually written it correctly. Sometimes I say things opposite. And that's grams of iron. Okay, so take a minute to breathe, because those are the marathon problems. And that marathon problem can have probably, they generally will have 3 or 4 little parts to it. Step 1 is usually find the limiting reagent. And that's the part that's hardest. It takes some time to think about how much I have of both, and figure out how much I need of both, and then just logistically kind of compare those. And then after that, it'll say, how much of X product can I make, which we went to copper, but it could be to anything. And they could use the molarity again, like to figure out liters or grams or moles. And then it'll say, how much of this excess do I have left over? So remember, use this as subtraction of what you needed to use from your original amount. Subtract and you can get to grams. And then sometimes it'll ask for, okay, I made blank amount. What's my percent yield? And what's percent yield again? Percent yield. Actual yield over theoretical yield times 100. So that's usually the 4th type of question. All right, you guys have problem set 12. 22. Yes. Have problem set 12 out. I want you to look through, and even look through the partner. Look through that, and I want you to determine which ones are the LR problems and which ones are not the LR problems. So you need to try to identify first how do you approach these problems. That you need to figure out who's LR and who's not. If you don't have problem set 12, I'll pull up on the board. You got extra? Oh. I have a whole nother problem, but I'm going to wait and do that later because you don't have the brain power right now for it. Label which ones are LR and which ones are not. It's going to be helpful later on. And maybe walk back through your notes to see if you have questions about your process. You need to look back through your notes. All right, how about number 1? Look up here now with me. If you have it on your desk or in your phone, that's fine. Number 1, that one's easy. I'm not even looking for it. Oh, I'm taking attendance yet. Number 2, is that one you want to see your agent at night?
No.
Is it low? Yeah, I got you. Sorry, thanks. number 2 limiting reagent? No, because it gives you moles of aluminum. No other distracting information. Sometimes you'll see, now this is the word we saw last or Monday, we were like, what does excess mean? Now we know. 88.4 grams of aluminum react with excess oxygen. When it says excess, you've already done all of this, right? So they're telling you excess is oxygen, so who's obviously the limiting reagent? Aluminum, but hey, you don't have to worry about it because it starts you off with that grams. You just truck to moles, truck to your final answer. These are easy now because they're already giving you who to start with because that's the only given to you. So you really think you don't have any other options. What number 3? Not a limiting reagent, so it's saying grams collected from that much iron and excess copper, blah, blah, blah. Okay, those are the easy ones. Keep going. Do you see a limiting reagent one yet? 1 through 5? Okay, so I'm hearing 7. You're looking at 7. Consider iron 2 nitrate according to this, blah, blah, blah. Determine the, okay, that's obvious because it says determine limiting reagent. So, what I'm going to task you tonight is, I want you to do, from your problem set 12, you should have already probably done some of the true false, you should have started a couple of these. I want to see fully complete 5 of the questions that are from the problem solvers down the bottom, at least 1 limiting reagent one. Okay, so I need to see at least 5 questions done of your choice, so you can see there's lots of options here, the answers at the bottom. I need to see 1 limiting reagent one. And so if you see the word limiting reagent, or like for example number 9, that's a limiting reagent one because it's giving you grams of aluminum and moles of iodine, but you need to do at least one of them for me tonight. So if you've already gotten ahead because you've done some, just make sure you're doing 1 LR for me, and that should be good for me. So in terms of stoichiometry tomorrow, what I'll do is I'll ask for you guys to keep bringing in some items. Stoichiometry is a limiting reaction lab. And if you've not done any limiting reagents for me, you cannot participate in the lab because you haven't done your part to pull your weight to make sure that you're fully competent to do the lab with this. Okay? It's a yummy lab. And if you need to talk to a group, so your groups you guys will be choosing tomorrow, if you're like, okay, Jacob, man, you're going to bring the chocolate, I'll bring the marshmallows. You want to talk to somebody, I already have a number of you guys brought some things in. But we always run out of chocolate. That is the limiting reagent. It goes fast. So if you're trying to think about what to bring, tell them to bring chocolate. We need to bring things like individually for our groups. So you guys are going to be working groups on each other. Okay, that's why we're getting blank for that.
Son, are you gonna be here for school, man?
I'm here for tutoring after school, specifically for you. AP doesn't need me. You need to come see me. Yes, the answer is yes.